A capacitor is a device that stores electrical energy, and it sort of looks like this. It actually stores electrical energy in the form of an electrostatic field. So, let's see how this works. In order to do this, I'm going to start by building a very simple circuit. So, I have an LED strip here. This is going to give us some light when we connect it to electricity in the right direction. So, let's see here. I'm going to start from the positive side. We'll go over here. And what color do we feel like today? Maybe blue? Let's do blue. And we'll connect this back to the power supply. Maybe we'll give it a little bit more. All right, and there you can see we have some blue light. You can also see when I disconnect it from the power supply on either of these sides, it immediately goes out. The response is instant, basically. All right, now we're going to connect the capacitors. I'm going to grab a couple more wires over here. And I'm going to take one side here. So negative side, that's this black wire, is going to go here. And I'm going to connect this to the negative side of my capacitor. This is an electrolytic capacitor, so it needs to be connected in the proper direction. So, okay, negative side of the capacitor there. Then I'm going to take the other side of the capacitor, this is the positive side, and I'm going to connect it over here to the red wire. All right, our capacitor is now hooked up. And in fact, it is now charging. In fact, it's probably pretty much charged by now. What I'm going to do is I'm going to disconnect our power supply, and we'll see what happens. And isn't that interesting how instead of being an immediate change when I pull this out, it slowly dies off. And in fact, don't even think that the power supply is involved in any of this, because I can completely disconnect it and it keeps on glowing. Why? Because the capacitor is storing electrical charge. And that charge is slowly discharging into this circuit, and you can see it's still barely glowing here, but that electricity that was stored in the capacitor is now powering the circuit. When we put this back, it will charge the capacitor back up, and we can do it again.
Well, aloha, everyone. Today, we're going to talk about capacitors.
In its simplest form, a capacitor is actually pretty easy to understand. All it is two metal sheets that are separated by a certain distance. One of them will get a positive charge, and one of them will get a negative charge. So I can build a very crude capacitor by taking two sheets of aluminum foil and making sure that they don't touch. So this is a capacitor. However, it's not a very good one. Why? Because the distance between my two plates is very large. We can solve this problem by adding a layer of clear plastic sheeting to this. This is an insulator, which will keep the two pieces of foil from touching. But we can still press down on them to make sure that they're separated by a very small distance. So this capacitor still isn't very good. Why? Well, because the distance between them is still very large compared to some of the commercially made capacitors. Also, this sheet actually isn't very large. So if we remember the formula for a capacitor, we can see that the bigger this sheet gets, the bigger the area of this overlap gets, the more capacitance we will have, the more charge we'll be able to store. And secondly, the closer these two layers get together, the more charge we'll be able to store. One of the ways that people sometimes will solve this problem is to try and make this sheet as thin as possible. They will try to make the metal foil as thin as possible, and they will compress it sometimes. So what we're going to do is we're going to put a sheet of foil, or a sheet of this plastic, over the top of this. Now, in order to compress these together, usually all that happens is this gets rolled up and compressed. So we're going to very carefully roll all of this up. And try to compress it as much as we can as we do so. Once we're done rolling it this way, we can roll it this way. And now we have a rolled up package that looks sort of like a cylinder. Kind of like that.
Okay, so now that we've seen how capacitors act in a circuit and how capacitors are made, let's get into the little nitty-gritty of it and figure out what capacitors actually are and how to calculate things with them. So, the first thing we want to talk about is a diagram of our capacitor. Remember, all it is two sheets of metal that are stacked sort of like a sandwich. So we have two plates, something like this. Pretend I'm drawing three-dimensionally here. They're separated by a certain distance. Sometimes they'll call this R, sometimes they'll call that D. Really doesn't matter what you call it. It's just the separation between the plates. So know that both of those are out there. And they each have a certain area. So the surface area of each of those. And if they're not overlapping, it's the overlapping regions. The parts where they overlap is the area we're talking about here. Okay. So if you want to know how good of a capacitor you have, your capacitance measures how good your capacitor is. And that is equal to, well, there's going to be a few things that are going to be important. In the little activity that we saw that the capacitor had a better ability to hold charge when it was larger. If you made the plates larger, it could hold more charge. So leave a little bit of space over here, but area is going to be very important, and it's going to be directly proportional to the capacitor's performance. Divided by. You also noticed that you could hold more charge when you stuck the plates closer together, because then positives would attract negatives, and they would be held there in place better. So it's inversely proportional to the distance between them. The closer you get those two plates together, the better capacitor you can make, the easier it is to hold charge. Then we have another piece. This is going to be epsilon naught. And this is called the permittivity of free space. You can think of it as related to how hard it is for an electric field to go through an empty space. So we're assuming right now that this capacitor has nothing between the plates, it's just air. The permittivity of free space is equal to 8.854 times 10 to the negative 12. And it's got these kind of crazy units on it. Coulomb squared per Newton meter squared. Yeah, kind of crazy units. But we'll see how that sort of works out eventually. So permittivity of free space is going to be how hard it is for an electric field to move through an area. But it turns out that's empty space. So we need one more piece. You saw when I was constructing that capacitor that I used a sheet of plastic in order to keep the two pieces from touching. Well, that's pretty common. It's not just plastic, though. Sometimes ceramic is used. Sometimes oil is used in capacitors. And other times there's even electrolytes that are used that form a very thin layer, about 1 molecule thick, of something like aluminum oxide that doesn't conduct electricity. So if there's something other than empty space between those plates, we need to account for that. And so we have something called, we use the letter kappa, and this is the Greek letter kappa, sort of equivalent to an English K, but it is what we call the dielectric constant. So if you take a piece of plastic or something, plastic, and if you take that piece of plastic and you insert it into your capacitor so that it keeps those two pieces from touching, now that plastic is called the dielectric. It's the insulator in between the two pieces. And it will have a certain constant. Some of the dielectric constants will be 0, 0.5, 0.7. Some will be 2. Some will be, I don't know, 3, 4. Could be all the way up to 7, 12, 15. I'm not sure what the highest dielectric constant we know is. But, usually it's a single-digit number in there. Okay, so now we have capacitance is equal to kappa epsilon naught A over R. A, of course, is area. Should have been writing this. Area. And, of course, R is the distance between them. Distance between the two plates. Okay, so we know how to build a capacitor. And we know we can make a capacitor better by messing with 3 of the possible variables here. To make the greatest capacitance, you are going to need the largest area you possibly can, the smallest distance of separation you possibly can, and a material with the highest dielectric constant you can find. That's how you make a good capacitor. But okay, what does a capacitor do? What is its performance? Well, capacitance, even though we know how to calculate it, what's its definition? By the way, these capital C's are for capacitance. And capacitance is about the ability to store charge. It's about the ability a capacitor has to store charge. So the capacitance is defined as mathematically Q over V. What is Q? Q is the amount of charge stored. By the way, that's on the positive plate. And V down here is the voltage applied. Or the potential difference between the two plates. So if you think about it, if you connect this to a 1.5 volt battery, you'll get a certain amount of charge that will build up on these plates. The bigger your capacitance, so as capacitance goes up, for that 1.5 volts that's staying the same, the amount of charge you get is also going to go up. So for the same amount of voltage, you get more charge that is stored by that capacitor. That's what makes a good capacitor. Okay, so let's see a simple example here and see what happens. Let's say we have 2 plates. I'm not drawing this very well. Let me try that again. So let's say we have 2 plates here. There's 1, and broop, 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 broop. There's 2. My drawing is not to scale because we're going to make this distance here. Let's make these square. And each of these sides is, I don't know, let's make the math easy, 1 meter. So it's 1 meter on each side. And let's make them separate by I don't know, how about 1 millimeter? And in order to keep them from touching, let's say that we take, I don't know, let's take a piece of ceramic. And we're going to insert this piece of ceramic in between the two plates. Like so. Okay, well, we need to know the dielectric constant of the ceramic. So let's see here. All right, so I just looked up the dielectric constant of different types of ceramics, and it turns out there is a huge variety of them. And it turns out I wasn't totally informed when I said that it's usually 3, 4, 5. For ceramics, the dielectric constant can be anywhere from about 5 all the way up to close to 10,000. So that dielectric constant is incredibly variable for different types of ceramics, and apparently it's pretty high for certain special formulations that we know how to make now. So I'm going to use a piece of ceramic. Let's say that it has a dielectric constant of 10. We're 1 millimeter apart. We have 1 meter on each side of our square. And I'll give you one more piece of information. We're going to attach this to a 9-volt battery. So over here, we're going to draw our battery, and we're going to attach one side here, and we're going to attach the other side here. And I want to know how much charge will build up in the capacitor. All right, so the first thing we've got to do is we've got to figure out the capacitance of this object. So I'm going to start with the formula. C is equal to kappa. Sometimes you'll see people just write this as epsilon, but the College Board writes it as kappa. C is equal to kappa times epsilon naught times A over R. So C is equal to, kappa was 10, times epsilon naught is 8.854, times 10 to the negative 12, Coulomb squared per Newton meter squared, times, let's see, A, well, that's the area, so it's 1 meter times 1 meter is 1 square meter, divided by the distance between the two plates is 1 millimeter, which is 1 times 10 to the negative 3 meters. All right, plug that into our calculator. Actually, we don't need a calculator for this because it's all ones. So it's going to be C is equal to 8.854 times 10. Let's see, so we have a positive 12, or yeah, negative 12, times 10 is negative 11. And then move it 3 more is 10, 9, 8. So 10 to the negative 8. And our units here are a little bit crazy, but check this out. So we have a meter squared here and a meter squared there. We have a Coulomb squared over a Newton meter. So this is coulombs squared over a Newton times a meter is a joule. So it's really coulombs over joules. Coulomb squared over joules. So capacitance is equal to 8.854 times 10 to the negative 8. And I'm going to manipulate this a little bit more because I know something. I know 1 volt is equal to 1 joule per coulomb. So if I look at that, then I know the inverse of a volt, 1 over volt, is equal to 1 coulomb over joule. And I see a coulomb over joule here. Actually, it's a coulomb squared over a joule. So I can turn that into a coulomb over a joule, which would be a volt on the bottom, and there's still a coulomb on top. So it's coulombs per volt. So C is equal to 8.854 times 10 to the negative 8 coulombs per volt. We give that a special name. We give the unit coulomb per volt 8.854 times 10 to the negative 8. We call that farads. We abbreviate that with a capital F. All right, so we have found the capacitance of this capacitor. Now we just need to go on and figure out how much charge this thing is going to store. So I know C is equal to Q over V, which means Q is equal to C times V. This is equal to, our capacitance was 8.854 times 10 to the negative 8 farads times, and our voltage was, it's a 9-volt battery, so 9 volts. Q is equal to, okay, so let's look at our units before we do anything. A farad, if we remember, was a coulomb over a volt. And, oh, look at this. Volts here. Bam, bam. We're left with coulombs. So we're happy because charge should be measured in coulombs. And now all we have to do is plug in the numbers into our calculator. So 8.854 times 10 to the negative 8 times 9 is going to be 7.96, call that 9. 7.969 times 10 to the negative 7. So we have a charge of 7.969 times 10 to the negative 7 coulombs stored in our capacitor. So that's really all there is to it as far as capacitors go, at least single capacitors go. So mahalo for watching, and see you next time.